I work for a company called RedTrack. We have a lot of data. I talked to my storage guy the other day, and he said that we were presenting about 1.2 petabytes of database data across a few hundred databases. So, and if you are from RedTrack in the marketing department, I apologize for not actually getting this onto the approved slide template. Who am I? My name is John Melesky. I'm a longtime developer, programmer. Last several years I was spent dealing with data in the cloud, and particularly a very popular cloud service provider, which is not very well conducive to databases for various I/O constraint reasons. Now I'm a database administrator. I've made that switch, and I get to use actual machines and actual disks, except that the machines are actually VMware instances and the disks are actually a NetApp storage system. But it's still like way, way, way better. I've got nothing but good things to say about both of those technologies. So let's jump right in. So you guys know what partitioning is, right? None of this code looks at all unusual to any of you. You know, you create your data, you create your table, your parent table, and you create some child tables on that are going to be partitions. You have your check constraint to make sure that constraint exclusion gets used by the planner. So it's all good. You know all of this, right? So back before we had that available to us, back in other database systems, there was a SQL compliant way of doing partitioning. And it involved a technique called union all views. Does anyone remember having to use this? Anyone actually have to use this before? Got a couple of people. And the way it works is pretty simple. You set up your partition tables, similarly, right? You just make sure they have identical schemas. And then you set up a view, which is using the union all operator to join those tables together. Well, not join, but slap those tables together. And you've got one view which looks at all of those tables at once, right? It's pretty nice for what it is, but it's, there are a lot of limitations. For one, this is a view, it's not a table. So you can't put an insert trigger on it, right? So you break the encapsulation that your developers are used to, where they can insert stuff into a partition table and it goes to the right place. Now they've got a view and they've got to decide where to insert stuff and all of that fun stuff. You can't use your inherent index shortcuts and stuff like that, which make managing object inheritance partitions relatively easy and straightforward. They're basically a bunch of shortcuts that are missing. And ultimately, in Postgres at least, the object inheritance partitioning is just a lot better supported. There's a lot more going on there than in the union view world. So we've more or less forgotten about it. Yeah?
Didn't 9.3 fix the first one?
I still haven't been able to. Oh, well, you know what? I was using in early beta for a lot of the testing for this. Right. Oh, so the question is, can you didn't 9.3 fix the insert trigger problem for views? And the answer is that it may have done. You can now put triggers on simple views. I don't know if this sort of view counts as a simple thing. All right, so I'm going to topic jump here. And this is the 10-second overview of what a foreign data wrapper, or how to set up a foreign data wrapper in Postgres to point to other Postgres nodes. All right, we've got, so make sure that you create your extension Postgres FTW. That's all you have to do on 9.3 because it's part of the normal contrib, assuming that you can compile your contrib modules in. On 9.2, there's a separate Postgres FTW module available from PGXN. 9.2 foreign data wrappers are read-only, but for the purposes of what I'm going to be talking about here, that's actually not a huge limitation. And then and for the record, you do this on your primary or your head node, right? The one that you're actually going to be doing your federated reads from. And then per data node, you create a server. This is a foreign data wrapper server. Right? And then you create a user mapping. Now this is, the first one's pretty straightforward. It's just a reference in Postgres for helping manage connections and all that fun stuff. The user mapping is, I've got this user in the primary database, and I want it to read as this other user in this other database, or read and write if you're using a read-write wrapper. For the purposes of this sort of setup, I'm managing all of these identically, so I'm having the same users both on the primary node as on the data nodes. There are situations other sorts of situations you might be using the Postgres foreign data wrapper in that you might actually want to create a more detailed user mapping. And then for every table that you're pulling in, you create a foreign table. You actually have to repeat your full table definition. That's not fun, but it's necessary. Point it at the right server object, which you created up there, and then you include any options. And one of the options that I'm including here is the table name. So I can have an identical schema on all of my data nodes. They all have a table called transactions, and they all have a table called users. And then I map them into my primary database as transactions underscore node 0, node 1, node 2, node 3, et cetera. And then users underscore node 0, 1, 2, 3, et cetera. There are plenty of other ways of managing that. A lot of people like to hide this sort of table in a separate schema. That's fine. Do whatever you need to. But that's the minimum that's necessary to move forward with using foreign data wrappers in Postgres. We create our federated view in the same way that we did the union all view locally on local partitions. In this case, we're unioning all over every one of our data nodes. Right? And we're done. I had this brilliant flash of insight one night at like 2 in the morning. I was like, I can get these queries to go everywhere at once and come back and it'll be grand. And then I actually tried it, and that's the rest of my talk. So querying is pretty straightforward, right? Select count from transactions. Transactions is now our view, which is going across all of these nodes. We've got different foreign scans. Foreign scan on each one of these data nodes. It obviously continues further down. The planning cost is very low, which is pleasant if you've ever worked with federating systems. Oftentimes they get a little complicated, and the query planning can suffer. And very importantly, there's a verbose argument to explain, which will actually tell you the query that it's sending to your data nodes, which is really, really useful for debugging things. And select null from amounts to a select count star. So it's doing a select count star from all of these data nodes and adding up the results. And when you actually run it, it does its thing. And it takes 3 seconds to go over 8 data nodes on my local laptop. All right, so I'm going to talk about a few general federating strategies. Just going to cover them briefly because I want to get enough background so that we can talk about what good strategies would be to apply to this sort of fairly limited situation. One is round robin. You'll see this a lot. I think if you've worked with Stato or you've read the Stato docs, you've seen that round robin is one of the federation strategies that they recommend, and that's where you, on each of your data nodes, you modulate your ID, or you do something where you're sending, the first row goes here, second, third, fourth, and so on and so forth. Right? You're not doing any data-aware partitioning. You're saying, I want to send my query to all of these nodes so that all of these nodes can do similar work in parallel and come back. Any questions on that? There are some problems with this. This is a little preview, and you can go ahead and take a look at that. And I'm going to gloss over it and come back to it later. Domain-based or list-based, this is also called. This is a popular use of the phrase sharding nowadays, where you have a partition. Each partition is defined by what values of a given field are in it. Not necessarily a date range, but you put the big customer on one node, you put some other customers on a couple of other nodes, and all of your other customers get slapped onto the end, right? For example. This is another very common federation strategy, and the intent is for each query to hit one node and come back. Right? Range-based, this is the same as range-based partitioning. Each node takes a range of data, for a given data field. It takes control over a range of the data. So your time-based partitioning all goes through this sort of thing. We're just extending it to be on the node level rather than an individual table file. Right. And table-based. Right. So this is a federation strategy where you actually have different tables living on different nodes. And this is a tricky one to plan for, but again, the intent is to hit a minimum number of nodes for each of your queries. Or if you've got a very strong federating system, to do some magical cross-node joins. Any questions so far? No? And then in sort of an orthogonal sense, you have multi-headed strategies, right? Where you've got more than one read node that are looking at all of these data nodes. And one of the nice things about the foreign data wrapper setup is that you can do this potentially quite a bit, right? Each one of those head nodes is creating a single connection per process to your data nodes. And that's fine because your users aren't hitting them directly, they're hitting the head node. So you spread out the read processing load among your head nodes and also spread out the read processing load among your data nodes. And this works with any of the federating data storage strategies that I mentioned earlier. This works with round robin, this works with range-based, et cetera. All right. But what you guys really want to see is this. You want to see this in action, right? Right? Okay. I mean, I don't have to if you guys don't want to. All right. So I have a 8-node setup. It's set up in a round-robin fashion. These are /DES shows you all of the foreign data, foreign servers that you're connected to. So you'll see I have 8 data nodes. I've actually also created a connection back to itself. So the primary database is foreign data wrapping itself for a single table. I'll get into why I did that a little later. There's no functional need for that. I'm just doing that for a particular demo. /DET shows you all of your foreign data tables, right? These are important PSQL commands to use. If you didn't know about them, you would want to look them up. And you can see that I'm federating 2 separate tables, transactions and users. I'm federating both of them in a round-robin fashion. So if I go ahead and connect to node 1 or node 0, as I mentioned, these are all running on the same node. You normally wouldn't be able to do this, but let's see. Right, you'll see these are all multiples of 8. And the same holds true on node 1. They're multiples of 8 plus 1. and so on and so forth. And when I go back to the primary node, if I you'll see because I limited the output, it visited its first data node, grabbed the 10 that it had, and gave those to me. If I were to order by ID, that would take a little longer. Right. But it comes back. So let's talk about some limitations. So network traffic overhead is an issue, even on a single node system. So I've actually got a copy of this data in a local table on the primary database. Boom, comes back very quickly. Now, if I create a foreign data node, or foreign data wrapper, to the same database, and create a table, foreign table, that points to this local table, it's just 10 million, or 1 million rows in a, 1 million rows in a table, it's on the same machine. It takes a little longer, because it's managing a connection. Right. So network overhead is actually a big deal, even in a situation where it's talking to localhost. And if I go to the actual federated view, so this is going to 8 different nodes, that completes pretty quickly. About the same speed, oddly enough. That wasn't working that way in my earlier tests. That's fine. Cache sensitivity is obviously an issue when you're dealing with 9 databases on a single node. Let's see. We've got network traffic as an issue. Dumb queries are a problem. Right? So this is the same query I was doing earlier. It's issuing a pretty simple query to each node. It's pulling back data and just slapping it together, adding it up. If I take the average int value, now it has to go through, and instead of giving me an easy count to append to each other, or to add together, I'm actually getting all of the int values back. Right? If this were a super smart federating system, then it would know that average can be broken down into count and sum, and maybe it would do that on all the data nodes. This is not that smart. And in fact, if you run it, it takes a little while. Well, that looks a little faster. Maybe it's doing something a little. Nope, it's doing the same thing. So dumb queries are a problem. Right? What do you think this is going to do? It's a pretty simple query, right? Group by something. It's grabbing every single type from users. Right. It's not pushing that down. The grouping doesn't get pushed down. Users is a fairly small table, though, so this doesn't take too long. transactions with a million row table, that would take a lot longer. So dumb queries continue to be a problem. Joins. You see how the queries get pushed down. Any guesses on how joins are handled? Anyone? They're aggregated? All the data is brought back, the join is done in the parent. So this is a fun query here. So we're actually doing a join across transactions and users. Users, of course, is a federated table. Transactions is a federated table. Sadly, this is not copy pastable. So this looks pretty straightforward, right? Get the user IDs from the transactions. And then it actually goes back to the users table, selects the ID from there with the where clause. It is pushing down the where clause. It knows enough to do that. And then doing a big hash join. And this, unsurprisingly, takes a little while. In fact, I'll come back to it. Keys, primary, foreign. Keys on federating systems is actually a really hard problem. I don't expect the Postgres foreign data wrapper to solve this. Primary keys are tough because you're splitting your table up into a bunch of different places, so you can't easily quickly check to see. Foreign keys, obviously, even harder because the table that you're referencing is split all over the place. Oh, that only took 3 seconds. That's not too bad. Indexes. You can certainly put indexes on all of your managed tables, all of your federated tables, on each data node. But have you ever tried to create an index on a non-materialized view or any view prior to a recent version upgrade? Correct. So you can't index on your primary node. Correct. So the point that was made is that on a partition system, you can't create an index which spans all the partitions, which is true. You can, however, simplify your index management rather significantly by setting up your partitions to inherit indexes from the primary table and create indexes against that table. You can't do that in the federating stuff that we're going over here. All right, now I want to bring you back to a slide earlier. You remember when I just threw this up here? So if you've got 8 different nodes and you're using them in a round robin fashion, you want to be able to ensure that on every given node, only the appropriate IDs are there. And you can do that on the node. When you create your table on the node, you can say, this is your check constraint for that table. On the foreign data table, you can't do that. Check constraints are not supported on foreign tables. What that means is the planner doesn't have access to your check constraints. In other words, if I even just go for a single user ID, it has to check all of them. Yeah. that hurts a lot of strategies. If you can't exclude what nodes you're hitting in your queries, then you're hitting all of the nodes all the time. It means you have to be very careful what indexes you put on your nodes. You want to make sure that you cover them so that they can respond quickly when they have no data relevant, which of course increases the overhead of index management. And it means that some of these bad queries, the dumb queries that we're sending, the joins, for example, are pretty hopeless. Right? You can't join a user table against, say, a date-ranged partition table that has 3 billion transaction entries and expect that to come in back in any kind of reasonable time. So the question is whether you can use a subselect to check only against the range of interest. And the answer is, of course you can, but the planner doesn't realize that that range of interest is only going to be on a single node. Right? So it's still going to query all of the nodes. You can query against a single node. Right? So if I know that if I know that user 123 is going to be on node 3, then I can actually target node 3, right? But that sort of makes the point of federating it in the first place a lot less relevant. Right? When you're not able to use your tables transparently and get the exclusion behavior they're expecting, you're running into a lot of situations where you have to write a lot of manual SQL. And the last limitation is that the executor on your head node is single-threaded. Right? How many nodes do you have? Do you know what they're doing? Let's see. We had a... Forgive me for mislabeling my time UTC table, or UTC column. It's actually timestamp without time zone, which, is a horrible thing that you should never do in production. Is it len or length for length of a string? I'll find out. It is length. All right. So this is the plan for that. It's obviously going to go through every single node. And I'm just going to set this up over here. We all know about the PG stat activity table. Someone loves it. Right. Pretty straightforward query against that table. And if we actually start running this, we'll see the horrible magic that I'm talking about. All right, well, we've got one active there.
You know about watch?
I do. Oh, all right, so that only took a few seconds. Well, 12 seconds. The material point there, and I'll go ahead and do this again. So we've got one active, we've got one active, no active, one active, no active, no active, boom. This is the problem with the single-threaded executor, right? If you've got 8 nodes, it's making 8 trips, and it's making 8 trips in sequence, not in parallel. So, according to the crowd, this may be an argument for DB-Link. I'll leave that for a different talk. So I'm going to now talk about strategies. We talked about some of these strategies earlier that are sort of generic federating strategies. I'm going to talk about some of them as they work with these particular limitations. So the first one is the large working set, small node strategy. Right? So if your working set is very large and you only have access to small nodes, but you've got a lot of them, right? And your network is faster than disk access, this might be worth looking into. This is a situation a lot of people find themselves on in certain cloud providers, where you've got a sort of a maximum amount of RAM that you can use for a given node. You can't freely add more RAM to it, but you want to make sure that all of your working set is in RAM rather than on disk, and you've got more predictable network access than you do disk access. It's an odd situation, but there are places where that all of those conditions hold. And in that situation, you can set up whatever federating strategy you want. You know that you're going to hit all the nodes. It's sort of like having a Mongo cluster, right? You know that your performance is going to tank as soon as you start having to hit disk for your reads. And you don't care that all of your queries are really, really sloppy. Another strategy, node-level partitioning. So you take your normal partitioning strategy and slap it across nodes. This is obviously hamstrung by the fact that you don't have constraint exclusion. So as a rule, like if you have a really big table and you want to do node-level partitioning on it, you probably don't want to do it over, in your normal partitioning strategy. However, if you've got a situation where you've got a big, beefy machine and you want it to handle the stuff that's going to be hit most often, and you've got maybe a couple of older machines, slower disks, whatever, that are going to handle all of the data that no one's going to be looking at, as long as you've got things indexed properly so that those indexes stay in the old machine, the archive machine's RAM, and they can respond fast enough to say they're irrelevant, this might be a viable strategy for you. I've got a few maybe nods going on out there. Yeah. I hope you didn't come to this being like, oh man, this is going to be great because this will solve all of our problems. This is not a strategy which solves all of our problems. Question? Correct. Constraint exclusion does not occur, so yes, you hit every node every time. So the situation where you win in this case is although constraint exclusion doesn't work, you can get fast responses if there's no data there, right? If there's no relevant data there, as long as it's hitting an index where it can tell the primary node there's no data there very quickly. So what's the advantage of having this over having all of these on a single node? Sometimes you can't put them all on a single node. That's the only advantage. Yep. So, according to someone who's read the Green Plum patent, I have not, so if I recreate their work, it is completely, whiteboard. According to someone who's read the Green Plum patent, their patent centers around having a coordinator node which makes intelligent decisions basically about constraint exclusion, right? And, would be great if it worked, and it might be great if Postgres could put those smarts into their view definitions, but we'll see. Another strategy: heavy distributed processing. Right? So you've got a lot of processing going on that's actually chewing your database cores. Right? You can take advantage of having a lot of CPUs available by spreading all this work out. This only works well if your workloads are discrete per node. Right? So you have to think very carefully about what your data nodes are going to look like. And you want to conform those data nodes to what your processing workload is going to be. And then you can have a whole bunch of processing going on at the same time, and they're all hitting their own nodes, and they're all chewing different cores, which is handy. Lock management can be a bit hairier. Right? I don't know if you've ever had the problem where you've got something that's been holding a lock for an hour, right? And it's holding up all of the processing in your database. Oh, come on, someone has had to have had this problem other than me. Thank you. If you're dealing with that and you've got multiple databases that could conceivably be holding that lock, actually figuring out what backends to cancel or terminate, or even what developers to go and talk to can be a bit hairier. But this might actually be a useful use case. Right. The prior one, less so. The prior one, probably not. But in general, this might be a useful use case, depending on what your workload is. Multi-headed, so where you've got multiple read nodes and multiple data nodes. It's like replication, but you've got no overhead, right? No delay. There's no replication delay between your master and your replicant. I mean, there is some overhead of network, and obviously you're now contending for the same resources. However, there's also no storage overhead. Disks are really, really expensive, right? Still, this might work well with the heavy processing setup. So you've got your processing happening, chewing up cores on a bunch of data nodes, and you've got a whole bunch of different read nodes that are all hitting things. It might work well. I haven't tried it. I can't vouch for it, but it might work well. And in fact, given the overhead that has to happen for each head node, given all of the stuff that they have to suck in and then calculate to do even a simple join, like we saw, this might be the only way to really get mileage out of this strategy, is if you have a bunch of these things all doing that kind of work. Some advice, no matter what strategy you go with. Think very carefully about what tables should live where. What tables should be federated? What tables should live on the head node? In my example, where I've got a few thousand users but 1 million transactions, that users table should probably live on the head node. And that would have simplified that join significantly, right? It would still have to pull all of the data back from the transactions table, but it wouldn't have to do a messy federated stuff on the users table. It would just have that stuff available to it on the head node. So figuring out what lives where is actually a thorny issue. Think very carefully about your tuning settings. Your primary node, your head node, is going to look different from the vast majority of databases you've ever tuned. Right? Your work memory is going to have to be big. Shared buffers, obviously, you're going to have to pay attention to where it is, not just sort of aim large, because you're now contending with your work memory. Temporary buffers is actually an issue you might run into. Probably not, but you might. Think very carefully about how many data nodes you want. 128 is probably too much. Right? This goes counter to the strategy that you hear from a lot of federation systems, where they say, create as many nodes as you want, or as many nodes as you think you might eventually use, and slap them on individual machines. Right? You don't want to do that in this case, because it's a round trip for each one. Think very carefully about your timings. Is your network fast enough to do this? Is your disk slow enough to make it worthwhile? How much is the overhead of the queries being not very bright going to cost you? What do your queries look like right now? There might be some query rewriting you have to do in order to really take advantage of this. And in case you can't tell, the thrust of this is think very carefully before you do this. Have a staging environment where you can try it out. That's my talk. Thank you. Any questions? Oh, you who's not there. Do you actually use this approach? I do not. I do not use this approach. Why don't I use this approach? Because the system that we're using, it's actually very easy to add almost infinite storage. We can increase the size of our storage mount points very easily. We can add more storage mount points for old partitions. We can do all sorts of stuff. And we can add CPUs dynamically because we're using VMware. So all of the use cases that I would have right now in my current job don't actually fit with this strategy. My last job where I was using EC2, I would consider this, but I would do a lot of research before going forward with it. Any actual questions? So the question is whether constraint exclusion is, if fixing constraint exclusion on foreign tables, or even enabling a constraint exclusion on foreign tables, would increase the number of use cases, and I think it would, right? It would make things, it would make it so that your thoughts about trade-off and network hops and number of nodes would, all of those questions would become much simpler. So yes, I do think that would expand the potential use cases. We had someone else back here first. Mm-hmm. Oh, so the question is about chewing on multiple cores for heavily processing systems and whether that runs into the sequencing, the multi or single-threaded execution system. And the situation where I'm talking about chewing on multiple cores is where you're connecting to an individual data node directly rather than connecting to the head node and doing processing there. Right? So if you're doing a lot of manual summarization, for example, if you're creating a lot of materialized views, which you're then federating, that's a situation where that might be a worthwhile thing. But in a situation where you're trying to federate that query, that's not going to be a win. Other questions?
Can you help function on if you have, say, a project table that you have some function that returns just information that you want to do? I guess, could you take a query and push it out ahead of time so that later on you could call it and get only the answers you want?
So the question is, can you write functions and integrate them somehow so that they send out the query to a useful query to all the data nodes, compile the results, and then have those results available for querying? And the answer is yes, and if you manage to do it, you can make a lot of money because it's a hard problem.
I was just sort of thinking about how would you get window functions to be useful in a setup like that. And that was the first thing that came to mind.
Right. So window functions and common table expressions are going to have to go through the give me all the possible relevant data process first. And is there a way to make that faster? I mean, I mentioned some things like you can optimize average to get count and sum, and then calculate your average afterwards on the node. Things like that are potentially optimizations that you could write in. But if you're talking about doing a general purpose query rewriter distributor, that's actually a hard problem. And it's possible, but again, if you manage to do it, you'll make a good amount of money because there are a lot of people who are really interested in sharding Postgres in that way. One more in the back. So the question is, what happens when you have a communication problem, right? So your head node loses its connection to one of the data nodes, and you have a query that's supposed to run against all the data nodes. Honestly, I don't know. I haven't run into that problem. My guess is, since the connection management is all in Postgres, in the foreign data wrapper itself, that it attempts to reconnect, and if it doesn't, then the query fails. There are systems where if the data node goes down or the data node becomes inaccessible, then you're going to run queries against less data silently. I don't think that's the case here, but don't quote me on that because I haven't actually run into the problem. It is not fault tolerant? Oh, never mind. Don't quote me on that because it is not fault tolerant. So another use case brought up is where you're doing a whole lot of inserts, and presumably updates as well would also benefit from this. You can spread those inserts and updates, your write I/O, across a bunch of different data nodes if you're planning appropriately. And I agree, that's also, I think, an interesting use case that's worth exploring. It's related to the sort of CPU saturation use case that I mentioned. It's just, instead of saturating CPU, you're saturating your disks. In the back? Okay. So there's so you work on PL proxy, you said? Right. So PL proxy is a situation where they've seen the problems of distributing federated queries that we're seeing now, and they've started to do things like automatically send the writes to different nodes as appropriate. And they're looking into, I'm just rephrasing this here, you're looking into using the V8 engine to actually run some asynchronous JavaScript to deal with the synchronous, the single-threaded execution problem. So I think that's probably a worthwhile project to look into. I don't know much about it, but I will certainly Google it this afternoon. So the question is, if you've got a single, or if you've got a cluster Is it worthwhile to have multiple Postgres processes reading from that cluster simultaneously? Well, and I think it can be done. I think that's one of the reasons why I suggested that the multi-headed system might be worthwhile, right? Because distributing the overhead of having the queries be not very bright, I think is a place where you can really get some good leg out of this particular technique. Is that the sort of thing you're talking about, or are you talking about?
Yeah, sort of as a general question, how do you feel about that kind of approach?
I think it's worthwhile to look into. I think it's less worthwhile for the type of work that I'm doing right now because we've got such dynamism in both our storage and CPU overhead. But in a situation where you are limited in node size, you're limited in RAM capacity, any of those constraints apply that might prompt you to look at this situation, having multiple read heads, I think, is a worthwhile thing to consider. Because there really is a lot of overhead that has to happen if you're the node in charge of all the reading. In fact, if you're doing this on an EC2 cluster, if you're stuck on Amazon Web Services, and I would recommend that your head node, don't make it a traditional sort of big RAM database node. Consider looking at the cluster compute stuff, right? It's got very high I/O, by which I mean network, and it's got a whole lot of processing power. And both of those things are going to be more relevant to you than having a huge RAM base or SSDs, for example, on the head node. On the data nodes, you want to have big RAM. Right. Any other questions? I don't know what my time is at this point. All right, so any other questions? All right. Thank you very much. I want to do a quick plug. There's someone else, Stephen Frost, is going to be doing another talk on using Postgres FDW to manage sharded systems. We've talked. He's actually contributed code to Postgres, which I have not managed to do. I think he might have been recently made a core committer. Yes, there's some verification of that. And he's going to be talking not just about some of the problems that I ran into, but also about directions that Postgres development might take in the future to mitigate those problems. So I do recommend you, if this is an interesting topic to you, definitely go to his talk. One other plug, Rentrack is hiring programmers, sysadmins, DevOps. We are not currently hiring any more DBAs, but I'm happy to talk to you about this. And with that, again, thank you very much for having me.